So here we are in lecture 26 in real analysis at the end of a long road that we've traveled together. I think this is our final official lecture for this course, and we're going to finish the proof that we were doing in the last lecture, and we're also going to discuss L'Hopital's rule. And once we've done this, I think that justifies basically every theorem used in calculus that involves just the first derivative. So we've come a long way in laying bare the inner workings of the calculus. All right, anyway, so continuing from last time, we were in the midst of proving a theorem. So the theorem was this one. We have an injective function on an interval, and so we have an inverse function on the image of that interval. And we're supposing that our function is differentiable and the derivative is never zero on this interval. Then the conclusion is that the inverse function is also differentiable on that image, and the derivative of the inverse is the multiplicative inverse of the derivative of the original function. And it's the derivative of the original function's multiplicative inverse when evaluated at the inverse point. So this C here is in the image of this interval, so we have to sort of go back to the domain of f by using the inverse function and then evaluate the derivative of our original function there. Okay, so it wouldn't really make sense to evaluate this thing at C because it's in the image, not in the original domain of the function. So we just have to hop back to the original and evaluate f prime there and do the inverse. Okay, so that's the formula. And last time we did a calculation that suggested that this formula was correct. There were just a couple things that we had to justify to make that calculation fully legitimate. The main thing is that we needed to know that the inverse was continuous. So not that surprising because we're trying to prove that the inverse is differentiable, which is going to imply that it's continuous. So it's not all that surprising. We need to know that it's continuous in the first place to see that it's differentiable. So that's kind of the main big point. And then another point also is that in order to do the limit to find the limit that defines the derivative of this inverse function at this C in this image here in f of this interval, we defined our derivative by having a two-sided limit. So we talked about derivatives at a point as long as it's in the interior of an interval. So it's not entirely obvious that this image of this interval is an open interval itself. So it could be that the image of this interval is like a half-open interval, and this C could potentially be kind of an endpoint of that interval. And in that case, our derivative wouldn't really make sense the way we've defined it. So we should probably justify that this C in this image is always surrounded by other points in the image. Okay, so what we'll show is that this image is in fact an open set. Okay, and since f is continuous, it's going to be connected, so it's going to be a connected open set. It'll be an open interval. Okay, so we're going to show that the image is open and that the inverse is continuous. And the main point to show that the inverse is continuous is to use a theorem that we proved last time, which is that if you have a function which is monotone and has the intermediate value property, then it's continuous. So we're going to show that the inverse function is monotone and has the intermediate value property. So the intermediate value property will be simple. Showing that f inverse is monotone is actually going to follow from the fact that the function f itself is monotone. So the remaining thing to do essentially is to show that the function f is monotone, and that is going to also imply that this image is open. So that really leaves, so the main technical point is to show that our function f is a monotone function. It's strictly monotone, so that is strictly increasing or strictly decreasing. So what we have here is this f is an injective continuous function on this interval. We'll show that any such injective continuous function, so the only way you can be continuous and injective is by being strictly either strictly increasing or strictly decreasing. So that ends up being kind of the sticking point that we need to justify. So as I said, B here, that immediately implies that F inverse is continuous by what we proved previously. So once we have B, we'll have this. As I indicated, we're going to get B from A, so F inverse being monotone. That's going to follow from F itself being monotone, and this item A will also imply that the image is an open set. So really what we need to prove, the big thing is to prove A. Once we have A, that's going to imply that the image is open, and once we have A, that will imply B. So we need to show we have A, that A implies that the image is open, and that A implies B. And that will complete the proof of this theorem. So first we're going to prove that an injective continuous function on an interval is strictly monotone. So the straightforward way to try to prove this is by contradiction. So if you have a function, or maybe by contrapositive, so if you have a continuous function which is not strictly monotone, then it's not injective. That's actually not going to be the way that we prove it, but I'll explain why it's not going to be the way we prove it, even though it's sort of the most straightforward way to do it. So if your function is not strictly monotone, then you have some points x1 and x2. So let's say x1 less than x2, where, so if it's not strictly monotone, then it's going to be increasing. So increasing for 2 points and then not increasing for some other 2 points, say. So it's going to be increasing like this for x1 and x2, but then decreasing. And of course, if we had equal to here, that would automatically tell us that it wasn't injective. So we'll just consider the strict case. Okay, so if you have this set up, you can basically try to use the intermediate value theorem to show that the function is not injective. So the idea would be something like if you have x1 and x2 and then y1 and y2, let's say your function value increased from x1 to x2, so maybe it was there, it increases to there, and then it decreased from y1 to y2. I just realized that that should say y1 there. Sorry about that. So then maybe it from here down to here. And so you can kind of see the way this function would have to go. Since it's a continuous function, it would have to be something like this, right? And then you would have a contradiction to injectivity. And you could make that precise with the intermediate value theorem. So in this case, the way I've drawn things, your f of x2 is between f of y1 and f of x1. And so because of that, well, that means your f of y1 is bigger than your f of x2. And so that means your f of x2 is a value between the values f of x1 and f of y1, and therefore by the intermediate value theorem you have to hit the value f of x2 somewhere between x1 and x2. And x2 in this picture is to the right of y1, so you have two values which are hitting the same f of x2 value. So in this case, right, we have this value here, and we have that value there. But the kind of trouble with this argument is, well, it's perfectly correct for this configuration of points, but there's different ways that this can be configured. The x1, x2, y1, y2 could have different configurations, so y2 could be, in here, and then the f values could have all different configurations as well. And so trying to figure out how to handle all of those cases becomes kind of annoying and laborious. It's the same type of argument over and over again, but I don't really see a particularly clean way to do all of those cases at once. But thankfully, there's a clever argument that obviates the need to do any of that. So here's what we're going to do instead. So we're going to define, so the basic idea here is we'll look at, so when x is less than y, we want f of x, so we either want f of x minus f of y. We either want this to be strictly greater than 0, so that says that our function is always increasing, or sorry, that would say our function is always decreasing, or less than 0, and that would say our function is always increasing. So what we're going to do is just define this function here, g of xy equals f of x minus f of y on this set of points here. So we're going to have the set A of xy points such that x is less than y. All right, so that's the basic idea. We'll define A to be the set of xy in R2 such that x is less than y, and we'll define g, so g will be a function from A to R by g of xy equals g of x, sorry, not g, f of x minus f of y. So I have two claims about these things. So we claim, first this set A, we have the line x equals y in R2. So this is a line x equals y. If you decrease your x from this line, that gives you this set over here. And pretty clear from the picture that this set is connected. And actually stronger than that, it's path connected, which is to say for any 2 points in here, it's pretty clear that the straight line between the two of them is also going to remain completely in that set. And given that, and that's easy to check. So all you have to do, if you take x1 and y1 and x2, y2 in A, then the straight line path between them is 1 minus t times x1, y1 plus t times x2, y2. So if we say gamma of t is that, then this is a continuous function from, so gamma is a continuous function from 0, 1 into the set A, such that gamma of 0, well, maybe I should make this, maybe I'll make this x0, y0, and then x1, y1. And then this satisfies that gamma of 0 is x0, y0, and gamma of 1 is x1, y1. And gamma here is continuous. So I guess that's also a claim that would have to be verified. So you need to verify that this gamma is continuous. And then if gamma is continuous, then what we have is we can connect any 2 points in A by this continuous function. And as you saw on the last problem on your second exam, if a set has that property that you can connect any 2 points with a continuous function like this, then it must be connected. So A is connected here. And the second claim is that G is continuous. So we claim that 1, A is connected, and 2, G is continuous. The second claim is simple as well. So G of xy, this is f of, this is basically a composition of functions. This f of xy is a composition of continuous functions. This pi 1, this is the projection of this pair of points xy onto the first coordinate. So this takes xy to x. Okay, and the claim is that that function is a continuous function, then minus f of the projection onto the second coordinate. So if these pi functions are continuous, then we have compositions are continuous and the difference is going to be continuous. So that would show that g is a continuous function. So you really just have to show that pi I, so you take the function pi I, which takes a point in Rn and spits out the ith coordinate. In fact, this is a uniformly continuous function. So you just need to check that pi I is uniformly continuous. And this just follows from the fact that the difference, so if you take 2 points, you take your pi I of x, so pi I of x, pi I of y, that's the ith coordinate, the difference of the ith coordinates of each, and that's less than or equal to the length of the difference vector. So any epsilon challenge, you can just take epsilon equals delta. So that's all easy stuff to verify. Okay, so relatively straightforward lemmas here will show that your A is connected and G is a continuous function. So I'll leave those as kind of exercises. Okay, and then given this, the rest of the proof is simple. So given this, given these facts, so we have a connected set and a continuous function on that connected set, the image must be connected. So given these facts, G of A as a subset of R is connected. But also note that 0 is not an element of G of A. And that is because G is an injective, the F is an injective function. If G were ever 0, that would say we had 2 different points, x less than y, such that f of x equals f of y, and that would contradict injectivity. And so this is because F is injective. And now we just use the characterization of connected sets in R, which says that if you have any 2 points in a connected set, then every point in between has to be in there. So if negative and positive values were in this G of A, then 0 would have to be in G of A, but 0 is not in G of A. So therefore, thus we cannot have both positive and negative values in G of A by the characterization of connected subsets of R. So thus, G is greater than 0 or G is less than 0, i.e. x less than y implies, so if G is greater than 0, that says that f of x is bigger than f of y, so that's f of x bigger than f of y, and f is strictly decreasing. Or f of x is less than f of y, and f is strictly increasing. And that's the proof. So moving on to the next item on the list, we have, again, our injective continuous function on this interval, and we're going to show that the image of that interval is open. So the proof is, well, since f is injective and continuous, it is strictly monotone. And we'll say that f is strictly increasing for definiteness. The other case would be similar. So the decreasing case is analogous. So the basic idea here is if you have your interval AB, we have C in here. We want to say that the image is open, so we look at f of C over here. And, well, C is in this open interval, so there's some little delta neighborhood that fits around it. So C plus delta, C minus delta. And what we can do is look at, say, sort of halfway here, C plus delta over 2 and C minus delta over 2. We can look at their images over here. And since this function is strictly increasing, we have to have f of, so this is going to be f of C minus delta over 2, and then we'll have f of C plus delta over 2. So we have things in the image which are below and above our f of c, but then the intermediate value theorem is just going to fill out everything in between. Right, so that'll tell us that we have some open set around here, right? So we have some open interval around here, and I guess they don't have to be evenly spaced. So I guess this f of c plus delta over 2 can be all the way out here, but in any case, we'll be able to find an epsilon that goes around this f of c and remains in the image. And so that's a simple outline of the proof. That's the picture that goes along here. So what we have, so take C in AB. So we need to show that the interval, so the f of c minus epsilon, f of c plus epsilon fits inside the image for some epsilon greater than 0. Okay, so since the interval AB is open, there is a delta greater than 0 such that the interval C minus delta, C plus delta is sitting inside AB. And these C minus delta, C plus delta, this could be A and this could be B, so we can't really consider F of those, but we can consider C plus delta over 2 and C minus delta over 2. So since F is strictly increasing, F of C minus delta over 2 is less than F of C, which is less than F of C plus delta over 2. So that's immediate by the intermediate value theorem. The interval, closed interval, f of c minus delta over 2 to f of c plus delta over 2 is contained in the image, is contained in f of AB. So then we just letting epsilon equal the minimum of, we can just take f of c minus f of c minus delta over 2 and f of c plus delta over 2 minus f of c. We clearly have that the interval f of c minus epsilon f of c plus epsilon is contained in the image. And that does it. That completes the proof. And so now to our final implication. This theorem then is going to complete the proof of the theorem that we had started last time. So we have a continuous and injective function on an interval, and then we're looking at the inverse function. The conclusion is that this inverse function is strictly monotone, and it has the intermediate value property, and therefore it's a continuous function. So we saw how well, not even strictly, just monotone function with the intermediate value property must be continuous. So here's the proof. So since f is continuous and injective, it is strictly monotone. And again, we'll say it's increasing, strictly increasing for definiteness, the other case being similar. So then we claim if your function itself is increasing, then the inverse is also increasing. So we claim that f inverse is strictly increasing. And so for this, we'll take y1 less than y2. So these are going to be in the domain of f inverse. So that's why I like to use y. So label the things in the domain of f with x, and then things in the domain of f inverse of y, just helpful psychologically. So we'll let y1 be less than y2, and suppose that f inverse of y1 is bigger than f inverse of y2. Well, these f inverse of y1 and f inverse of y2, they're now in the domain of f. They're in AB. Well, f inverse of y1, so the f inverse of yi are in AB, and f is increasing. So if we just apply f to these 2 points in AB, since this point is to the right of this point, the value of the function here is going to be bigger than the value of the function here. We obtain f of f inverse y1 is bigger than f of f inverse y2. But this is, right, the f and the f inverses cancel out. This is y1 bigger than y2. And this contradicts, so contradicting y1 less than y2. Okay, so thus we must have f inverse of y1 less than f inverse of y2. Of course, the inverse function is injective, right? So f inverse, if you have an inverse, you have to be injective and surjective. So we can't have the equals case, got to be strictly less than. Okay, so that's the monotone property. And so f inverse is strictly monotone. Okay, and as I said, the decreasing case would be an entirely analogous argument. So now we just have to show that that F inverse has the intermediate value property. So to see that F inverse has the intermediate value property, we'll continue to assume that F is strictly increasing, that F and therefore F inverse are strictly increasing for definiteness. So what we can do is, so suppose that we have F inverse of y1 is less than alpha, which is less than F inverse of y2, where necessarily here y1 is less than y2. So what we have here is we have these two elements of the interval from a to b, and we have this alpha between those two things. So alpha is also in the interval from a to b, and so what we can do is we can apply f to this to these two inequalities here, because f is increasing, so it's going to preserve these inequalities. So since F inverse of yi are in the interval from a to b, so is alpha. Thus we can apply f to F inverse y1 less than alpha less than F inverse of y2 and obtain y1 less than f of alpha less than F inverse, or sorry, not F inverse, less than y2, since f is increasing. Strictly increasing. But now we can just do the same thing with F inverse. So we can just now apply F inverse, which is also strictly increasing, but F inverse is also strictly increasing. So we have F inverse of y1 is less than F inverse of f of alpha is less than F inverse of y2. And see, we have in the middle here, this is just alpha again, right? F inverse of f of alpha is just alpha. So we're back to the inequality that we started with, but now we know that alpha is F inverse of something, and that something is between the y1 and the y2 that we started with. Right? This is exactly what we need for the intermediate value property. We have a value in between these two values, and we had to find something in between the two domain elements which hits that value. So now we have that. So alpha is equal to F inverse of f of alpha, and we know that that f of alpha is between y1 and y2. So thus, alpha equals F inverse of f of alpha, where y1 is less than f of alpha is less than y2. So the IVP is satisfied as claimed. Okay, so just returning to our to-do list, just remind ourselves that we completed the list. So we now know that an injective continuous function on an interval is strictly monotone, and we saw how that fact implies that the image of the interval is open, and we saw how that implies that the inverse function is monotone and has the intermediate value property and is therefore continuous. So we now know that our assuming we have an injective continuous function, the image is open and our inverse function is continuous. And so that allows us to conclude the proof of the theorem that we started with in the last lecture. So the computation that we did to show that the derivative of the inverse satisfies this formula, we just needed to know that the inverse was continuous and that it was legitimate to talk about the derivative at this point because it's because the image is an open set. Okay, so so our theorem here is complete, and that's that. But not quite in a way. There's just one more point I want to make, which is actually, in a sense, this theorem assumes too much because actually the assumption that our function has a derivative which is not equal to 0 automatically implies that our function here is injective. And this is just a simple argument with the intermediate value theorem. So if your function wasn't injective, if you had f of x equals f of y, then looking at f of x minus f of y over x minus y, that would give you, that has to be equal to the derivative at some point, and this should be 0, right? But we know that the derivative is not equal to 0. So in a way, we can make this theorem a little bit more streamlined. All we really have to assume is that our function is differentiable and has non-zero derivative. Then automatically the function is injective. We have our inverse, which is defined on this open set and is then monotone and therefore continuous. And so this derivative formula holds. So we can really make this theorem a little bit more streamlined in the assumptions in its statement. And that's often called the inverse function theorem. So I'll state that theorem for you down below. Okay, so here's the statement of the inverse function theorem. We have our function f is differentiable and the derivative is not equal to 0 on some interval. And then we conclude as we did above. So we have all the conclusions above and the additional assumption that we made above that f is injective. So actually we don't have to assume this. It just follows from the fact that f prime is not equal to 0. So our function is automatically injective then by the mean value theorem argument that I outlined. And then the image is an open set, and our inverse function is differentiable on that open set with derivative satisfying the formula that we discussed. So the proof here is simple. So the fact that f prime not equal to 0 implies f is injective follows immediately from the mean value theorem. From the MVT, and then the remaining claims follow from the propositions above. So the final topic I want to discuss from calculus is L'Hopital's rule. By the way, this is how L'Hopital himself spelled his name. I know there's different conventions for how to spell his name. I'll stick to this one. It was good enough for him. It's good enough for me. Apparently, French spelling has changed a bit since then, so you might see it spelled different ways, but this is my convention. So L'Hopital's rule, as you might remember from calculus, if you have... So the simplest case of it, anyway, is where you have two functions which are approaching 0 when you approach some point, and then you're looking at the limit of their quotient. And basically the rule tells you that you can just replace this quotient of functions with the quotient of their derivatives. That's kind of the version we teach calculus students. And for a long time I didn't have a good intuition for why this was true. I didn't have any particular insight into where this rule comes from. But I think the basic idea is kind of this, that if your functions, so you have your function f, it's sort of limiting to 0. So let's say this is going to be your a here. And you have your function g, which is limiting to 0 at a. The basic idea is that if you zoom in here, right, your function f is going to start looking like its tangent line, and the function g is going to start looking like its tangent line. So you can kind of replace these more complicated functions with just their tangent lines. And so that has something to do with the derivative. And so we can make this a little bit more precise with a kind of ad hoc calculation, or maybe I should say naive calculation. So if we take this f of x over g of x, well, our function is effectively 0 at a. So let's just assume our function actually takes the value 0 at a, so it's continuous at a. So you'd have something like, so f of a is 0, so I can just write this as f of x minus f of a over g of x minus g of a. And then you can kind of see the difference quotient coming in. So if we can just do something like, we can just insert an x minus a in there. So you have f of x minus f of a over x minus a over g of x minus g of a over x minus a. And then that gives you the derivative at a on top and the derivative at a on the bottom. And if f and g are if f prime and g prime are continuous at a, so if they're defined at a and continuous at a, then we can write this as the limit as x approaches a of f prime of x over g prime of x. So let me say this computation is going to be sort of a naive computation. Okay, so this legitimates the rule in a certain special case. So in order to make this computation, what we had to do is basically assume that our function was defined at a, right? So defined and continuous at a, and actually more than that, we assume that the function's derivative was defined and continuous at a. So in order to make this calculation, so this calculation assumes that f prime and g prime are continuous at x equals a. But in general, actually, this is a bit too strong. So this is a bit strong. So for example, if you take f of x equal to x to the 2/3 and g of x equal to x to the 1/3, then the limit as x goes to 0 of f of x over g of x, you can easily just directly compute that that is 0. And the limit as x goes to 0 of f prime of x over g prime of x, well, you can easily also compute that this is 0. Okay, so these are equal. Right, so we have equality of these limits despite the fact, so this is despite the fact that f prime and g prime are not even defined as 0. So this indicates that there's something a little bit more general going on with L'Hopital's rule. So we have a calculation that gives us the rule in a very special case, but it seems that there's something a little bit deeper going on, a little bit more subtle going on, because we can actually see instances of the rule that don't quite satisfy these stronger conditions on it. Before we move on to the rigorous stuff, though, I also just want to recall from calculus that L'Hopital's rule works in other situations too. So, for example, with f of x and g of x tending to 0 as you tend to a, you can actually replace a with plus or minus infinity as well. So for instance, the rule works when a is equal to infinity. And so this is kind of suggested by, so as x goes to infinity, if you set x equal to 1 over t, say, then this is sort of the same as t goes to 0, or t goes to 0 from the right, maybe, would be more precise. So what you can do is sort of change this limit into limit as t goes to 0 from the right of f of 1 over t and g of 1 over t. And then now you're back in the finite situation, so you can take the derivative with respect to t here and sort of and get the same result. So that's one extension of L'Hopital's rule. Other ones, you can also, as you know, there's other indeterminate forms. There's another indeterminate form that L'Hopital's rule applies to. So you can have, let's say, so if limit as x goes to a of f of x equals plus or minus infinity, and the limit as x approaches a of g of x is also plus or minus infinity, then you can apply the same, in exchanging the quotient for the quotient of the derivatives thing in this case as well. And so one way to make that plausible, so I'm just trying to make these assertions plausible, intuitive. One way to do this is you can just do a little algebraic trick. So g going to infinity, that means 1 over g goes to 0. So you can do 1 over g of x, put that in the numerator, that's now going to 0. And 1 over f of x, put that in the denominator, that's now going to 0. So now you're back in the situation you were before, where you have the function in the numerator going to 0, function in the denominator going to 0, and then you can apply the original L'Hopital's rule to this one. Or that's sort of that's the basic idea of making these extensions to other indeterminate forms. Just one last thing before we get to the statement of L'Hopital's theorem. We have to just make sure we're clear what we mean when we talk about limits that involve infinity. So there's a number of different permutations here. So we can have our x approaching infinity or negative infinity and have a finite limit. So this would just mean that our f of x is getting close to this finite number when our x is getting large. So this means for all epsilon, there's an m, so that when x is to the right of m, okay, so x is going to infinity, so x is going to be on the right, implies that f of x and L differ by less than epsilon. Okay, so f of x is close to L when x is to the right in the real line. And then there's a similar definition when you have negative infinity here. You just flip this inequality. So everything reads the same except x is less than m. Then we can also have a finite a here, so approaching a finite point, but our f of x is approaching an infinite value. So what this means is just that our f of x is arbitrarily large when x gets close to a. So for all m, our f of x is, we're going to say f of x is bigger than this m when x is close to a. So for any m, there's got to be a delta, so that when x is close to a, within delta of a, then f of x is bigger than that given m. If we switch infinity to negative infinity, then we're just trying to say f of x is smaller than any given value, so f of x would have to be less than this m. So you just switch switch the direction of the inequality there. And of course, we can also combine the infinity in the x and the infinity in the value. So we could have the limit as x goes to infinity of f of x equals infinity. And what this means is that f of x is arbitrarily large as x gets arbitrarily large. So for any m, we want our f of x, we're saying our f of x can be bigger than this m as long as our x is sufficiently big. So we have to be able to respond with a mu such that when x is to the right of mu, then f of x is to the right of m. And there'd be similar definitions for each of the cases, right? So you can put a plus or a minus on this infinity, you can put a plus or minus on that infinity. And so you have 4 cases in total. Switching the sign here just switches the inequality here. Switching the sign here switches the inequality here. Okay, so you have the 4 cases reflected in the 4 possible combined directions of these inequalities there. All right, so very much in the style of our normal epsilon delta, just reflecting sort of the obvious changes that need to be made for these to make sense. Okay, so finally, here's the statement of L'Hopital's rule. We have functions, f and g, which are differentiable on some interval. And this interval is possibly infinite. So our a could be negative infinity, our b could be infinity. Or maybe it could be finite as well. So any kind of open interval. And our denominator, g prime, so in this limit here, our g prime is not going to be 0, so this division makes sense. And we're going to suppose that this derivative limit is equal to L, right? So the quotient of the derivatives limit is equal to L, and we're going to try to conclude that the limit of the quotients itself is equal to L. And here our L could be finite or some kind of infinity. Okay, so interpreting if it is infinity or minus infinity, interpreted, right? So this only ever appears in this limit statement, so we interpret those infinities in terms of the definition that was just given. Then we have 2 possible scenarios. So if the limit of the f and the g are both going to 0, so we have a 0 over 0 indeterminate form, then it is the case that the limit of the quotient is going to L, right? So our limit of our quotient of our derivative is going to L. If we have a 0 over 0 indeterminate form, then the quotient of the original function is also approaching L. The other case, and this is a little bit maybe surprising if you've only ever worked with L'Hopital's rule in calculus, and actually I was a bit surprised to find this out myself first time, that you don't need so classically in calculus, you have the indeterminate form infinity over infinity. In fact, you really only need the infinity in the denominator. So you don't need the infinity in the numerator. Okay, so it could be infinity in the numerator. Basically, you don't need to really know anything about f of x. F of x doesn't even have to have a limit as you approach a. All you need to know is that the limit of the denominator is positive or negative infinity. And then if you have that, along with this limit condition, then the limit of the quotient is equal to L. Okay, so basically what you're used to from calculus, except with this novelty here of you only need to know something about the limit on the denominator if you're going to infinity. I should probably also remark on the fact that in our statement here we have x going to a, and our interval here is from a to b, so we're approaching a from the right. Everything would work here if we change this limit from as x goes to a to limit as x goes to b. So the same holds for limit as x goes to b also. Okay, so now let's look at the proof. So our first case is going to be where limit as x goes to a of f of x equals 0, which equals the limit as x goes to a of g of x. And here we're going to assume, so we're in this case here, we have we're allowed to suppose that the limit of the quotient of the derivatives is L, and we'll suppose that our L is finite to start with. Okay, so case 1a, we're going to also suppose that L is finite. So since the limit as x approaches a, so we're just going to start with what we know. So we have this limit. What that means is that once we're close enough to a, that the difference between this quantity and L is less than any given epsilon. Since that, for any epsilon greater than 0, we can so there is a C, so we'll say C in AB. This C is just A plus delta. Okay, so this C here is equivalent. So we're just saying we're close enough to A here. Okay, so C is going to be close to A, it'll be A plus delta. Such that when x is in AC, the difference between, so f prime of x over g prime of x minus L, that's less than epsilon and bigger than negative epsilon. All right, actually, I'm going to use t instead of x. Sorry about that. So we're going to have t here. And now the key thing is to use the generalized mean value theorem. So the generalized mean value theorem says that f of x minus f of y over g of x minus g of y is equal to f prime of t over g prime of t for some t between x and y. Okay, so this is the generalized mean value theorem. So if we take x and y in this interval from a to c, right, so take any x and y in there, then there's going to be a t in between those x and y, so that t is also necessarily going to have to be in AC, in the interval from AC. And then we'll have that this minus L is between epsilon and negative epsilon. That'll tell us that f of x minus f of y over g of x minus g of y minus L is also between epsilon and negative epsilon. Okay. So by the generalized mean value theorem, so that's generalized mean value theorem, GMVT, for any x and y in the interval AC, we must have, I can say we must then have f of x minus f of y over g of x minus g of y minus L. That's less than epsilon and bigger than negative epsilon. Note this quotient actually makes sense. G of x can't equal g of y because g of x, g prime is not equal to 0 in our interval. And we discussed how the mean value theorem implies that g has to be injective then on that interval. Okay, so this quotient makes sense. And so let's see, so what do we have? Well, what we're trying to get to is f of x over g of x, the difference between f of x and over g of x and L. We want that to be arbitrarily small. But what we're supposing is that as we approach A, f and g both go to 0. So what we can do here is we can take y, we can let y go to A. So taking y to A here, right, this is just going to shrink to 0, this shrinks to 0. We obtain, so this is by the order limit theorem. So by the order limit theorem, so we obtain that negative epsilon is less than f of x over g of x minus L less than epsilon. Actually, I should be a little bit more careful. This is going to be less than or equal to for any x in the interval from A to C. And so we're basically done here. We've shown that for any x in this interval from A to C, so you have C is A plus delta, the difference between f of x over g of x and L is is less than or equal to epsilon in absolute value. We really are supposed to get less than epsilon, but this is not actually a problem because for this given epsilon, we can find our delta, or we can find C, such that when t is within delta of A, this quantity is less than epsilon over 2 in absolute value. So I can just change this to epsilon over 2. That'll change this to epsilon over 2. And that'll change this to epsilon over 2. And this is now strictly less than epsilon, bigger than negative epsilon. Okay, so that gives us this gives us L'Hopital's rule in this case, where we have a finite L for this limit, and and we have a 0 over 0 indeterminate form. So the key thing is just the generalized mean value theorem. Once you have that, it's really actually quite simple. Okay, so the proof is not even that hard once you know the generalized mean value theorem. B, let's take a look at the case where L is equal to infinity. So suppose L equals infinity, and the negative infinity case is similar. So L equals negative infinity is similar. So what we have is, so since the limit as x approaches A of f prime over g prime equals infinity, for any epsilon greater than 0, or actually it's not epsilon greater than 0, it's now for any given m. So for any m, there is a C in AB such that when x is in AC, that implies that f prime of x over g prime of x is bigger than m. Or maybe we should, so probably what's going to happen is, like before, we're going to have to go back and modify our initial, so back in the previous case we modified our initial epsilon to epsilon over 2. So let me just, let me call this m prime. Or maybe I'll just, instead of m prime, I'll say, we'll just have some constant times m. Where k is some constant. We'll go back and fill that in. And once again, I realized I mislabeled here. I want to say this is t. So by the generalized mean value theorem, for any xy in AC, it follows that f of x minus f of y over g of x minus g of y, that's got to be equal to one of these f prime t over g prime t's, and so that's bigger than whatever our multiple of m is. So again, let y go to a and obtain f of x over g of x is bigger than or equal to our multiple of m. And so if we just take this k to be 2, that's strictly bigger than m then. All right, actually, I didn't say that my m was positive. Maybe I should have stuck with the m prime here. So I just need, if I take this m prime to be m plus 1, then m plus 1 is bigger than m. Okay. So in this case, we find that we can make this f of x over g of x arbitrarily large. For any given m, we can make it bigger than that m. And remembered something else. There's a reason I was phrasing, there's a reason I'm not using delta and I'm using c here. And that's because this a could be negative infinity. So saying it this way, that t is in some interval to the, starting at a and going to the right, that makes sense no matter whether a is negative infinity or finite. So we're just using language that kind of unifies those cases. Okay, so this essentially completes the proof of L'Hopital's rule in the first case. So now we're going to go to the second case. So case 2, we have the limit as x goes to infinity of g of x equals plus or minus infinity. Okay, so I'll first note that it suffices to do the limit as x approaches infinity of g of x equals infinity case, because you can just replace g with negative g. Okay, simple. So we first assume that our limit is finite. So let's take a look at what this means. So we have x approaches a, f prime over g prime equals L. Since that, for any epsilon greater than 0, we have, or I should say there is AC in AB such that when t is in that interval, that implies that f prime of t over g prime of t. The difference between that and L is less than, I'll say epsilon prime. We'll go back and fill in the appropriate epsilon prime later. So this epsilon prime is something that depends on epsilon in a way that we'll just determine in a bit. So by the generalized mean value theorem, now this is going to go slightly differently than before. This case is not as simple as the last case. That was not that bad or anything. So by the generalized mean value theorem, for any x less than y in AC, we have just that same inequality, but with that quotient replaced by f of x minus f of y over g of x minus g of y. All right, so somehow we want to go from this to f of x over g of x minus L within these bounds. So last time we just took y going to a, and right, we had our f of y and g of y going to 0, so those just sort of vanished. Now we don't even have a limit for f of y, and what we have is g of y going to infinity. So here's kind of the intuition. So basically, yeah, so in this case, we have our x less than y. So we're going to think about x. We're going to think about this x moving towards a. So in the classical case of L'Hopital's rule, you would have the indeterminate form infinity over infinity. So let's think for a second if f and g are both going to infinity as we approach a. Basically, the point would be that as x goes to a, our f of x is going to infinity, g of x is going to infinity. So f of x minus f of y, this y is just fixed. So as f of x goes to infinity, f of x minus f of y and f of x are basically the same. Right? I mean, they don't differ by that much, at least proportionally speaking. So even if f of y is initially, is some large value, well, f of x is getting really, really large the closer we bring x to a. So the difference between f of x minus y and f of x, if we look at the ratio of them, they're pretty close to 1. Those quantities aren't that different. And the same thing with g of x minus y versus g of x. They're practically the same. So as we bring x closer to a in that scenario, this fraction would basically be indistinguishable from f of x over g of x, because these f of y and g of y are not really making that much difference once f of x and g of x are really large. So that's kind of the intuition for the classical, infinity over infinity indeterminate form. But actually, we really don't need to think about f of x going to infinity. We really just need g of x going to infinity, which is the case we're trying to prove here. Because as x goes towards a, g of x gets very large, so g of x minus g of y gets very large, and therefore f of y over g of x minus g of y, that's getting vanishingly small. So we can basically kind of ignore that. And then, so that's going to go away. So now just focus on the f of x over g of x minus g of y. Well, again, that's basically just sort of like f of x over g of x, because g of x and g of x minus g of y are basically indistinguishable for this fixed y once x gets such that g of x is very, very large. Okay, so when this g of x is very, very large, the difference between f of x over g of x minus g of y and f of x over g of x, basically indistinguishable. Okay, so basically we just need to sort of figure out how to handle this, but that's kind of the intuition for what's going on, for how you can pass from this to that. Okay, so that's all that's kind of happening here at an intuitive level, at a rough level. And so it turns out the best way to rigorize this, to turn this into, into something you can actually work with, is as I said, the basic idea is that g of x is basically going to be indistinguishable from g of x minus g of y once g of x is very large, in the sense that the ratio of g of x minus g of y over g of x, this should be going to 1. And so what we're going to do is we're going to multiply this expression here by this quantity. So when we do that, the g of x minus g of y in the denominator cancels with that, and then we'll have f of x over g of x and f of y over g of x, and that f of y over g of x, that's going to go to 0, and so we'll be left with f of x over g of x, and then a bunch of other stuff that we can kind of handle. But this is the main trick, is to think about this quantity here, g of x minus g of y over g of x, and that's going to be sort of going to 1, and so if that's going to 1, we can multiply this whole inequality through by that without changing things too bad. Okay, so that's the basic idea. And in order to do that, so in order to multiply through by this quantity without changing things, we just need to prepare the way for that a little bit. We need g of x minus g of y to be positive and g of x to be positive to make sure this whole fraction is positive, which of course we can do because g of x is going to infinity. So, since g of x is going to infinity as x goes to a, there is a d in AC such that when x is in AD, g of x is bigger than g of y and g of x is positive. So for x in AD, we can multiply the inequality above by g of x minus g of y over g of x and obtain all right, so this is what you get after you do a bunch of simplification. So you multiply through by this quantity, do a bunch of simplification. It's boring. I don't want to bore you with it. You can just do it yourself. It's just some algebra. So you get f of x over g of x minus L. This is the quantity we want to trap. We have our epsilon prime minus epsilon prime, but then we have this, these wacky quantities here. Okay, so this looks bad, but actually you should realize that it's not. So I'll explain to you why it's not. These numerators here are just fixed numbers. So our y is going to be fixed. Our epsilon prime is something we've chosen earlier that's fixed, and this L is our fixed given limit in our problem, right? So this is just going to be some number, and g of x is going to infinity. So we can take our x further close to a, right? So we can just move closer to a and make this quantity completely insignificant, completely irrelevant. We can do the same with this quantity here. So all we need to do is take x a little bit closer to a such that these quantities are small. Okay, and we'll be in good shape. So basically the details here now are going to be, we just need to make this thing less than epsilon over 2, and this thing less than epsilon over 2, and we'll take our epsilon prime to be epsilon over 2. And then if this thing is less than epsilon over 2, then the sum of these two can exceed epsilon over 2, epsilon over 2 plus epsilon over 2, which is epsilon, and similar for this quantity over here. So I've gone and changed all the epsilon primes to epsilon over 2, and now we just have to note, since g of x goes to infinity as x approaches a, there is an r in AD such that when x is in that interval, the quantity f of y, so we have So looking at this quantity here, negative epsilon over 2 is bigger than that f of y plus epsilon over 2 minus L g of y over g of x. Right, we have to be able to make this thing close to 0, so it's got to be greater than whatever this negative epsilon over 2 is, and f of y minus epsilon over 2 plus L times g of y over g of x is less than epsilon over 2. So it follows that if x is in this interval AR, then negative epsilon is less than f of x over g of x minus L is less than epsilon. So we indeed have, so limit as x approaches A of f of x over g of x equals L. All right, so I'm kind of out of time here, and the proof of the other case where L is infinity or negative infinity is completely analogous. So the case where, or I guess maybe I should say cases where L equals plus or minus infinity follow the same basic computations. With the necessary changes being made. All right, and that's going to conclude the proof. So that's the main part of the proof, is just to see the different cases where your f and g are going to 0 as you approach A. It's just a simple application of generalized mean value theorem and then taking a limit, and then where your g of x is going to infinity. In that case, it's a little bit more of an involved application of the generalized mean value theorem. You can't just straightforwardly take a limit. You have to do a little bit more thinking and a maybe slightly clever algebraic manipulation. But then it turns out to not really be so bad. The computations look ugly, but they're really not all that bad once you kind of think your way through it. Okay, so I've gone on long enough here. I think this is our last sort of official lecture of content before the final. I think I'm going to have some kind of wrap-up video, some video sort of wrapping up the semester, but I don't think we're really going to have any more new content. So I just thank everybody for following along with these videos, and I hope you enjoyed and learned something. And I don't know, I'll see you next time if there is a next time.